And now let us try to combine the rules of inference for propositions and quantified statements. So the first rule that we have is the universal modus ponens, where it combines the universal instantiation and the modus ponens into one rule. So if you remember, the universal instantiation has this form. We have for all x, p of x, therefore p of c, wherein c is any member of the domain. Okay. While the modus ponens has this form, we have the P implies Q and P as premises, therefore Q. Okay, so we can rewrite it as P implies Q and P implies Q. Okay, so combining these rules into two, we arrive into this form. We have for all x, P of x implies Q of x. So this looks familiar to this. You have P implies Q, and we have the P of A, therefore Q of A. Okay. So if this is true, and the P of A therefore follows that this is also true, then we can say that Q of A is also true. All right. So we have, okay, so let us have this example. Let us show that these premises, everyone in this discrete mathematics na class has taken a course in computer science, and Marla is a student in this class, imply the conclusion Marla has taken a course in computer science. So the first thing that we have to do to determine the validity of this argument is that convert this into its argument form. And we can do that by converting this into propositional variables or predicate logic na form. So we should identify the individual na predicates. So let's say we have identified here d of x, in which x is in this discrete mathematics na class. So we have this. So this is the d of x. Okay, and x has c of x. X has taken a course in computer science. So this is, on the other hand, oops. Let me just, this, on the other hand, is the c of x. Okay, so we can then express this statement into for all x, d of x implies c of x. Or in other words, everyone in this discrete mathematics na class has taken a course in computer science. And Marla is a student in this class. Or Marla has taken a discrete mathematics na course, or d of Marla. So we can say that Marla is a computer science na student or has taken a course in computer science. Okay, so we want to use these premises in order to arrive to this conclusion, or to write it down. We have for all x, d of x implies c of x, and d of Marla, therefore c of Marla. All right, so let's move on. So the following steps can be used to establish the conclusion from the premises. So the first premise that we have is for all x, d of x implies c of x. And now we can use the universal instantiation for one, wherein we simply replace x with any value. For this example, we have Marla. So we have d of Marla implies c of Marla. So since this is true, we can say that Marla, for Marla, it is also true. Now we also have another premise that d of Marla. So by modus ponens and using this, we have for all x, P of x implies Q of x, and we have the P of C, therefore Q of C, right? So since D of Marla is true, then we can say that C of Marla is also true by modus ponens. Okay, let's have another example. All human beings are mortal, and we have another statement. Sachin is a human being. So does it follow that Sachin is also mortal? So now let's convert it into its symbolic na form. We have h of x. X is a human being, and m of x, x is a mortal. Okay, so we have the domain of discourse is all the human beings. So any human being can replace x. Now we can express this statement into for all x, h of x, all human beings are mortal. So we have the h of x, and this refers to the instantiation. And then we have mortal, so this is m of x, right? And then Sachin is a human being. So we have h of Sachin. So we have here then applying the modus ponens for all x, h of x implies m of x. Since h of Sachin, then it implies that m of Sachin, or since Sachin is a human being, it follows that he is also immortal. Now another version wherein it is more detailed. So we have this first, the premise, right? And then applying the universal instantiation. And we simply have to replace this with the x with Sachin, right? And since this is true, so it follows that for any human being like Sachin, that it will also be true. Okay, and then we have, since Sachin is a human being, then by modus ponens of 2 and 3, so we apply modus ponens to this, then Sachin is then a human being. Okay, now let's have another example. We have these premises. All lions are fierce. And some lions do not drink coffee. So can we conclude that some fierce creatures do not drink coffee? So now let us identify each of the predicates. So we have X is a lion, and then X is fierce, and X drinks coffee. So the first one is, let us do it one by one. So we have all, so meaning that for all X and then lion. So that means L of X implies then fierce, we have F of X. Okay, so this is the first quantification that we have. And then some, so we have there exists X, then lions, so that is L of X, and that do not drink coffee. So that's C of X. So we have there exists X. So this is the negation of C of X. So we have there exists X such that L of X and not of C of X. Now, some fierce creatures do not drink coffee. So we can deduce it as there exists X and fierce creatures. So meaning this is F of X, right? And do not drink coffee. So that is simply the negation of C of X. So we then have there exists X such that F of X and not C of X. So using this first two na premises, how can we arrive to this conclusion? Okay, so let us do it one by one. So we have here the first. So again, this is our premises, and this is our conclusion. Okay, so in here, you can start with either this quantification or this quantification, so long as you arrive to the conclusion. So in this case, we started from the second, the premise. So there exists x, L of x, and not of C of x as the premise. And using the existential na quantification of 1, we simply replace x with any value. So in this case, since this is true, so for some members of x, L of who, and not C of who. So this will be true. And then we apply now a simplification to 2. So if you remember the simplification, we have P and Q, therefore P, right? Or P and Q, therefore Q. So applying simplification to this, we have L of foo and not C of foo. So we have L of foo, simplification of 2, and the C of not of C of foo. And now we start with another premise. For all x, L of x implies f of x. And similarly, we can replace it with any value, say foo. So given that this is true, it follows that its specific instance is also true. Okay? And now, what we can do is apply modus ponens to 3 and 6. So this and this. So we have the modus ponens. We can rewrite it as L of foo implies f of foo, and we have L of foo. So therefore, f of foo. Okay, so essentially we are canceling this out, and we have therefore f of foo, and we evaluate to this statement f of foo, and now we can apply conjunction to 4 and 7. So for this and for this, we have the not C. So we simply end the 2. So we have f of foo and not C, not of C of who. So we simply apply or include a connective and, right? And then we can say that since this is true, then we can apply existential generalization. So since there exists a specific instance from the domain in which this is true, then we can conclude that the quantification there exists x, f of x, and not c of x is also true by existential generalization from 8. Okay. Now another example, a student in this class has not read the book, and everyone in this class passed the first exam. So someone has passed the first exam, has not read the book. So can we conclude that the statement is true given the first two na premises? Okay. Now let us identify the individual na predicates. So we have a student in this class, so we can have that as he of x. And then read the book, so we have b of x. And then passed the first na exam, so that is p of x. So then we can then express the first statement as there exists X, or there is a student in this class in which C of X implies not B of X, since they have not read the book. While the second is everyone in this class. So we have for all X, C of X implies P of X. Okay, so we then have there exists X, C of X implies not P of X, and for all X, C of X and P of X. And we have there someone. So there exists X who passed the first exam. So we have the P of X and not read the book, not B of X. Okay, so we have this universal quantification of form. Now, using these premises, how can we arrive to this conclusion? Let us move on. So we can start with this premise. Okay. There exists X, B of X, and not of B of X. Now we can apply existential instantiation by simply replacing C of X with any variable. Let's say A. So we have C of A and B of A. And we can apply simplification to this too. So we have C of A, or we can actually have not B of A, right? So again, we have the P and Q. Therefore, P or P and Q. Therefore, Q. All right, so we simply apply to that. So we have C and A. And now let's have another premise. We have for all X, C of X implies C of X. And now apply universal instantiation. We simply replace this X with A. So since this is true, it follows that for any member of the domain, the implication is also true. And next is we are going to apply Modus Ponens by 3 and 5. So we can apply Modus Ponens for this. So we have the C of A, and C of A implies P of A. So therefore, we have P of A. Okay, so that's why we arrived to P of A. And now we have this not of P of A. Where did this come from? So it is actually from this simplification of 2. Okay, and now we can apply conjunction to 6 and 7. So we have the P of A and not P of A. We simply connect them using the AND connective, and then we can it then follows that given that this in this specific instance, or for a specific person like A, P of A and not P of A is true. So we can then generalize that there exists P of X and not P of X as also true. Okay, remember we need only one person for this to be true in order for this quantification to be true. Okay, so it means that someone who has passed the first exam has not necessarily read the book. So you might have just read the slides or read the recordings. Okay, so that's a personal, not a part of the argument. Anyway, we also have the universal modus tollens